Welcome everyone. I am Nancy Preeta, Assistant Professor from the Department of Computer Science, St. Anthony's College of Arts and Sciences for Women, Dindigul. It's a great privilege for me to conduct the 5 days FDP on operating system, a step into problem solving for NetSet. I thank the management and express my deep sense of gratitude to our respected Secretary, Reverend Sister Margaret Inbasili. I am greatly thankful to our respected Principal, Reverend Sister Dr. Mary Pramila Shanti, for giving me this opportunity and for her guidance in the launch of this FDP. I am delighted in welcoming again each and every teaching faculty from various institutions for joining us, and I thank you all for your participation. An outline of day 1 session includes what is CPU scheduling, objectives of scheduling, different times with respect to a process, CPU scheduling algorithms, problems based on CPU scheduling algorithms. Before seeing what is CPU scheduling, let me give a short note. Usually we develop program codes using IDE and save those programs in local disk. Once we execute the program gets loaded into the main memory and we call that as a process. Hence we usually say the process is a program under execution. Many processes that are ready for execution have to be scheduled, and it is the task of an operating system to make the decision. So, what is CPU scheduling means? CPU scheduling is an operating system technique to decide which process will own the CPU for execution. One of the objectives of CPU scheduling is to maximize CPU utilization. Hence, the main task of CPU scheduling is to ensure that whenever the CPU becomes free, at least one process must be scheduled for execution. And coming to the objectives of scheduling, scheduling aims to maximize CPU utilization, to maximize throughput. Throughput is nothing but number of processes completed per unit time, minimize turnaround time, minimize waiting time, and minimize response time. We will see turnaround time, waiting time and response time in the next slide. Here we come across different times with respect to a process. Arrival time is the time at which the process actually arrives in the ready queue. Then completion time is the time at which the process fully completes its execution. Then burst time is the time required by a process for CPU execution. It can also be said as the total time taken by the process for its execution on the CPU. Then turnaround time is the time difference between completion time and arrival time. We can write that as completion time minus arrival time. Then waiting time is the time difference between turnaround time and burst time. That is, waiting time is equal to turnaround time minus burst time. Response time is the time when the process actually gets its first response. So these are all the different times with respect to a process, and we will use all these terms in CPU scheduling algorithms. So these are all the following scheduling algorithms we are going to see today, and let us see how to solve problems using those algorithms. Coming to first come first serve scheduling. Here process execution is done on first come first serve basis, which means a process which enters the ready queue first will be scheduled first. It's a non-preemptive scheduling algorithm, which means an operating system cannot stop or pause a currently executing process. It is easy to understand as well as it is easy to implement. It is implemented using queue data structure. Coming to the demerits, it has poor performance because average waiting time is usually high. One more demerit is convoy effect. Convoy effect is a situation where many processes who need to use CPU for a short time are blocked by one single process holding that resource for a long time. So this is known as convoy effect. Usually convoy effect can be removed by executing processes with lower burst time first, and this can be visualized in the next algorithm called shortest job first. Let us see how to solve a problem using First come first serve scheduling algorithm. Here the problem is given as consider the processes P1, P2, P3, P4 arriving for execution in the same order with arrival time 0 and burst time is given in milliseconds 21, 3, 6 and 2. We need to find the average waiting time using first come first serve scheduling algorithm. The concept used with first come first served is the process that arrived in the ready queue first will be scheduled first. So P1 will be scheduled first, then P2 will be scheduled, P3 will be scheduled, and finally P4 will be scheduled. Let us draw a Gantt chart now. Gantt chart is a horizontal bar chart developed in 1917 by Henry L. Gantt. Using this representation, let us see how to represent the start and finish of the processes. Let us draw the Gantt chart. Process P1 has arrived at time 0. So from 0 to 21 milliseconds, process P1 will get scheduled, which means that P1 will get the CPU first, then P2 will get the CPU, P3 will get the CPU, and finally P4 will be executed. P2 needs 3 milliseconds of execution, so 21 plus 3 is 24. From 21 to 24, P2 gets executed. Next P3. P3 needs 6 milliseconds for execution. So 24 plus 6 will be 30. From 24 to 30, P3 gets executed. And at last, P4 alone will be available in the ready queue. P4 needs 2 milliseconds for execution. So 30 plus 2 will be 32. From 30 to 32, P4 gets executed. We need to find the average waiting time using FCFS scheduling algorithm. Actually, this is the Gantt chart representation. Before finding average waiting time, let me give few captions. Process, burst time, completion time, turnaround time, which is equal to completion time minus arrival time. Then waiting time, which is equal to turnaround time minus burst time. Let me take the processes P1, P2, P3 and P4. The burst time of P1 is 21. The burst time of P2 is 3. The burst time of P3 is 6 and the burst time of P4 is 2. From the Gantt chart, the completion time for process P1 is 21. So, let me take the completion time as 21. For P2, from the Gantt chart, the completion time is 24. So, here it is 24. For P3, the completion time is 30. For P4, the completion time is 32. Turnaround time is completion time minus arrival time. So for process P1, turnaround time is 21 minus arrival time. Arrival time is 0. So 21 minus 0 is 21. Then for P2, the turnaround time is 24 minus 0, 24. For P3 it is 30. For P4 it is 32. Waiting time is equal to turnaround time minus burst time. So for P1, 21 minus 21 will be 0. For P2, 24 minus 3 will be 21. For P3, 30 minus 6 will be 30 minus 6, it will be 24. For P4, 32 minus 2 will be 30. So the total will be 30 plus 24 is 54. 54 plus 21 is 75. So total will be 75. Now we need to find the average waiting time. We need to find the average waiting time. So average waiting time is equal to sum of waiting times of all the processes divided by total number of processes. Average waiting time is equal to sum of waiting times is 75 divided by total number of processes is 4. Since there are 4 processes, this is equal to 75 divided by 4 will be equal to 18.75. Since the time unit is given in milliseconds, it is 18.75 millisecond. So this is the way how to compute the average waiting time using FCFS schedule. Let us see about shortest job first scheduling. This scheduling is non-preemptive, which means the CPU cannot be forcibly taken away from the currently executing process. The next thing, it is the best procedure to minimize average waiting time, and the concept used with the shortest job first scheduling is the process with shortest burst time will be scheduled for execution. Then coming to the demerits of shortest job first scheduling, it leads to poor service if the burst time is high. Then since it is non-preemptive, if a shorter process arrived later, then it has to wait, which leads to starvation. And it is difficult to find the length of the next CPU request. Hence, this algorithm is usually not implementable. So these are all the demerits of shortest job first scheduling. Now let us see how to solve a problem using shortest job first scheduling. This is the given problem. 4 processes were given, P1, P2, P3, P4 with arrival time 0 and burst time is given in milliseconds. We need to find the average response time and average waiting time using SJF. So before finding average response time and average waiting time, we need to draw a Gantt chart. As said earlier, the process that has the least burst time will be scheduled first. So in the given problem, P4 has the least burst time. It has only 2 milliseconds. So it will be scheduled first. Then P2 has the least burst time, 3 milliseconds. So after P4, P2 will be scheduled for execution. Then P3 will be scheduled. And finally, P1 will be scheduled. So the order of execution will be P4, P2, P3 and P1. Now let us draw a Gantt chart. From time 0 to time 2, the process P4 gets executed. Since P2 needs 3 milliseconds for execution, from 2 to 5, that is 2 plus 3 is 5. So from 2 to 5, P2 gets scheduled. That is not 3, it is 5. P2 gets executed in the time slot 2 to 5. Then P3 gets scheduled. P3 needs 6 milliseconds for execution. So 5 plus 6 will be 11. In this time slot, P3 gets executed. At last P1 is available. P1 needs 21 milliseconds for execution. So 11 plus 21 is 32. In this time slot, that is from 11 to 32, P1 gets scheduled. This is the Gantt chart representation for the given problem. Now we need to find average response time and average waiting time using SJF algorithm. In this table, the given processes were taken P1, P2, P3, P4. Then their corresponding burst times are also noted 21, 3, 6 and 2. We need to find completion time. From the Gantt chart, let us find the completion time. The completion time of process P1 is 32. So here we represent as 32. The completion time of P2 is 5. So represent here as 5. Again from the Gantt chart, the completion time of P3 is 11. So let me represent here as 11. Then the completion time of P4 is 2. So here it will be 2. Response time is the time at which the process actually gets its first response. Process P1 actually gets its first response at time 11. So here it is noted as 11. Similarly, P2 gets its first response at time 2. P3 gets its first response at time 5. So let me note here as 5. And P4 gets its first response at 0th millisecond. So here let me note as 0. Next thing we need to compute is turnaround time. Turnaround time is equal to completion time minus arrival time. For process P1, completion time is 32 and the arrival time is taken as 0. For all the processes, the arrival time is taken as 0. So 32 minus 0 will be 32 for process P1. For P2, turnaround time will be 5 minus 0, which is 5. For P3, 11 minus 0 is 11. For P4, 2 minus 0 will be 2 minus 0 will be 2. Now let us compute the waiting time. Waiting time is equal to turnaround time minus burst time. So turnaround time for P1 is 32 and the burst time for P1 is 21. Hence waiting time for P1 is 32 minus 21, which is 11. Then for P2 waiting time is 5 minus 3, which is equal to 2. For P3 waiting time is 11 minus 6, which is equal to 5. Then for P4 waiting time is 2 minus 2, which is equal to 0. We need to compute average response time and average waiting time. Let me find the total response time of all the processes. So here the total is 18. Let us find the sum of waiting times of all the processes. And here the total is 18. Now average response time is equal to sum of response times of all the processes divided by total number of processes. So average sum of response times of all the processes is equal to 18 divided by total number of processes is equal to 4. 18 divided by 4 is equal to 4.5 milliseconds. Then average waiting time is equal to sum of waiting times of all the processes divided by total number of processes. So here average waiting time is 18 divided by 4, which is equal to 4.5 milliseconds. Here the convoy effect problem in FCFS that lead to high average waiting time is thus reduced in shortest job first, because there the average waiting time is 18.75 and here it is 4.5. Coming to shortest remaining time first algorithm, it's a preemptive mode of shortest job first algorithm. Currently executing process can be preempted if a shorter process arrives at a later time and it leads to less average waiting time. Demerits: poor service if CPU burst time is high. Let us see a problem how to solve using SRTF algorithm. This is the given problem: P1, P2, P3, P4 and P5, and their arrival time and burst time are given in the table. We need to find average waiting time using SRTF. Let me draw a Gantt chart. At time 0, only P1 has arrived. No other process has arrived at time 0. So, from 0 to 1, P1 gets scheduled. At time 1, P2 has arrived. So, current execution of P1 will be stopped. Already P1 has executed for 1 millisecond. So, the remaining time for execution is 7. 8 minus 1 is 7. At time 1, P1 with burst time 7 and P2 with burst time 4 is available. Since P2 has the least burst time, it will be scheduled for execution. From 1 to 2, P2 will be scheduled. The remaining time for P2 is 3. At time 2, P3 has arrived. P3 has burst time as 2. It is least when compared to the remaining burst times of P2 and P1. So, P3 will be scheduled now. From 2 to 3, P3 will be scheduled. Remaining time for execution for P3 is 1. At time 3, P4 has arrived with a burst time 1. That is, if both CPU burst times are equal, then scheduling is done on their arrival times. So, P3 gets scheduled now. From 3 to 4, P3 again gets scheduled. P3 has fully completed its execution now. At time 4, P5 has arrived with a burst time 3. At this situation, P4 has the least burst time, so it will be scheduled now. From 4 to 5, P4 will be scheduled. P4 has completed its execution. Now at time 5, P6 has arrived with a burst time 2. When compared with the burst time of all the other processes, P6 has the least, so P6 will be scheduled now. That is, from 5 to 7, P6 gets scheduled. Now the remaining processes are P1, P2 and P5. P2 and P5 have equal burst time. In this case, since P2 has arrived earlier, it will be scheduled. P2 will be scheduled. So from 7 to 10, P2 gets scheduled. P2 has fully completed its execution. Then when compared with P1, P5 has the least burst time, so P5 will be scheduled. From 10 to 13, P5 gets executed. And at last, P1 is available with a burst time 7. So now P1 gets scheduled. 13 plus 7 will be 20. In this time slot, P1 gets executed. This is the Gantt chart representation of the given problem using SRTF. Let us find the completion time now. Completion time of P1 is 20. The completion time of P2 is 10. The completion time of P3 is 4. For P4, the completion time is 5. For P5, the completion time is 13. For P6, the completion time is 7. Next, turnaround time is equal to completion time minus arrival time. So for P1, turnaround time is 20 minus 0, which is equal to 20. For P2, 10 minus 1 is 9. For P3, 4 minus 2 is 2. For P4, 5 minus 3 is 2. For P5, 13 minus 4 is 9. For P6, 7 minus 5 is 2. Coming to waiting time, it's equal to turnaround time minus burst time. So waiting time of P1 is 20 minus 8, which is equal to 12. For P2, 9 minus 4 is 5. For P3, 2 minus 2 is 0. For P4, 2 minus 1 is 1. For P5, 9 minus 3 is 6. And finally for P6, 2 minus 2 is 0. When we compute the total, we get the value as 24. Now we need to find average waiting time. Average waiting time is equal to sum of waiting times of all the processes divided by total number of processes. So for our problem, average waiting time is equal to 24 divided by 6. This is equal to 4 milliseconds. Assume that all the time units were taken as milliseconds. So this is the average waiting time for the given problem using SRTF algorithm. Let us see priority scheduling. Priority scheduling can be preemptive or non-preemptive, and here each process will be assigned a priority. The process with highest priority will be executed first. Suppose if both the processes have same priority, then they are executed on first come first serve basis. The demerits for priority scheduling is starvation. The starvation will lead to indefinite blocking in case of low priority process. So the solution for starvation is aging technique. Aging technique is usually used to increase the priority of a process gradually if it spends more time waiting in the ready queue. Let us see a problem based on priority scheduling algorithm. This is the given problem. Consider the processes P1, P2, P3, P4 arriving for execution with arrival time 0 and priority 2, 1, 4, 3. 2 for process P1, 1 for P2, 4 for P3 and 3 for P4. And burst time 21, 3, 6 and 2. We need to find the average waiting time using priority scheduling algorithm. Here, generally lower the priority number, higher the priority of the process. So, the priority number for P2 is lower, so P2 will be scheduled first. Then the priority number for P1 is 2, so P1 will be scheduled next. Then P4 will be scheduled and finally P3 will be scheduled. Let me draw a Gantt chart. So from 0 to 3, since P2 has the lower priority number 1, it will be scheduled first. It needs 3 milliseconds for execution. So from 0 to 3, P2 gets executed. Next P1. P1 needs 21 milliseconds for execution. So from 3 to 24, that is 3 plus 21 is equal to 24. In this time slot, P1 gets scheduled. Then P4 will be scheduled. P4 needs 2 milliseconds for execution. Hence, 24 plus 2 is 26. In this time slot, P4 gets executed. And at last, P3 is the lower priority process. So P3 will be scheduled at the last. It needs 6 milliseconds for execution. So from 26 to 32, P3 will be scheduled. This is the Gantt chart representation for the given problem using priority scheduling. We need to find the completion time. For P1, the completion time is 24. So here let us take the time as completion time is 24 for P1. Then the completion time for P2 is 3. So here it is 3. For P3 the completion time is 32. So let me note here as 32. The completion time for P4 is 26. So here let me note as 26. Next, turnaround time is equal to completion time minus arrival time. So for P1, 24 minus arrival time. Here the arrival times of all the process is taken as 0. Hence 24 minus 0 will be 24. Then for process P2, turnaround time will be 3 minus 0, which is 3. For P3, the turnaround time will be 32 minus 0, which will be 32. For P4, it will be 26 minus 0, so it is 26. And coming to waiting time, it's equal to turnaround time minus burst time. So for P1, waiting time is 24 minus burst time is 21. So 24 minus 21 will be 3. For P2, 3 minus 3 will be 0. For P3, 32 minus 6 is 26. For P4, 26 minus 2 is 24. Computing the sum of waiting times of all the processes, we get the value as 50 3. So average waiting time is equal to sum of waiting times of all the processes divided by total number of processes. So that is 53 divided by 4, since there are 4 processes. This will be equal to 13.25 milliseconds. So this is the value for average waiting time using priority scheduling algorithm. Let us see round robin scheduling. It's a preemptive scheduling. Here each process is provided a fixed time for execution. We say that as time quantum or time slice. Process is preempted once the time slice expires. And here context switching is used to save the states of preempted processes. Coming to the demerits of round robin scheduling, if time slice is very small, then large number of context switch occurs. If time slice is high, then RR will just work like FCFS. So the solution can be 80% of CPU burst should be shorter than time slice. Let us see how to solve the given problem using round robin scheduling. 4 processes were taken with arrival time 0 and burst time. We need to find the average waiting time using round robin scheduling. Here the time slot is taken as 5 milliseconds. Now let us draw the Gantt chart. For every process, 5 milliseconds will be allocated. Once the time slice expires, the next process will be scheduled for execution. So here the order of arrival is taken as P1, P2, P3 and P4. So P1 needs 21 milliseconds for execution. Hence from 0 to 5. Why it has been taken as 0 to 5 means the time slot is only 5 milliseconds. So 5 milliseconds alone will be allocated for a process. Already P1 has executed for 5 milliseconds. So 21 minus 5 will be 16. Still P1 needs 16 milliseconds for execution. Process P2, 3 milliseconds for execution. So just 3 milliseconds alone will be allocated for P2. So from 5 to 8, P2 gets scheduled. P2 has fully completed its execution. Then P3, the burst time of P3 is 6. 5 milliseconds will be allocated for P3. That is from 8 to 13. P3 gets scheduled. Remaining P3 needs 1 milliseconds for execution. Then P4 needs only 2 seconds. So from 13 to 15, P4 gets scheduled. Now P4 has fully completed. The ready queue P1 and P3 is available. Now it is the turn for P1. P1 will be again allocated 5 milliseconds. So from 15 to 20, P1 gets scheduled. Remaining 11 milliseconds. Then in the ready queue P3 is available with 1 millisecond. So from 20th millisecond to 21st millisecond, P3 gets scheduled. Now P3 has completed its execution. P1 needs 11 milliseconds for completion. Now again 5 milliseconds will be allocated, which will be 26. Still P1 needs CPU for 6 milliseconds. Again P1 will be allocated 5 milliseconds. So 26 plus 5 is 31. From 26 to 31, P1 again gets scheduled. Remaining time is 1. Now from 31 to 32, P1 again gets scheduled. Now P1 has fully completed. So this is the way how the processes are represented using Gantt chart using round robin scheduling algorithm. Now coming to completion time. From the Gantt chart, the completion time of P1 is 32. So let me mark here as 32. Then the completion time of P2 is 8. So here it is 8. The completion time of P3 is 21. Let me note here as 21. The completion time of P4 is 15. So here it is taken as 15. Coming to the turnaround time, it is completion time minus arrival time. So for P1, 32 minus 0 will be 32. For P2, 8 minus 0 is 8. For P3, 21 minus 0 is 21. For P4, 15 minus 0 is 15. Waiting time is equal to turnaround time minus burst time. The waiting time for P1 is 32 minus 21, which will be 11 for P1. Then waiting time for P2 is 8 minus 3, which is equal to 5. Then for P3, 21 minus 6 is 15. Then for P4, 15 minus 2 is equal to 13. If we find the total of waiting times of all the processes, we get 44. So the average waiting time is 44 divided by 4, which is equal to 11 milliseconds. This is the average waiting time of the given problem using round robin scheduling. That's all for today's FTP. Thank you all.